In April 1945, Major General Curtis Lame faced a significant issue that was depriving him of sleep, bombers, and potentially jeopardizing the entire Pacific War. His B-29 Superfortresses, which represented the most costly weapons initiative in human history at $3 billion, surpassing even the Manhattan Project, were missing their targets by miles, not feet or yards, but miles. These were not just ordinary bombers. The B-29 was intended to serve as America's decisive technological advantage against Japan. With pressurized cabins, crews could operate comfortably at altitudes beyond the reach of Japanese fighters. The bombers were capable of flying higher, farther, and carrying more ordnance than any other aircraft in the sky. On paper, they appeared invincible. However, in reality, they were operating without effective targeting. The strategic bombing campaign aimed at Japan's industrial core was failing dramatically. Missions launched from the Mariana Islands, Guam, Tinian, and Saipan required crews to traverse 1,500 miles of open Pacific Ocean, locate a target the size of a factory complex in a darkened city, drop their bombs from nearly 6 miles above, and return home. More often than not, they struggled to even identify the correct city, let alone the specific factory. Lame's bomber crews adhered strictly to established protocols. They employed the same navigation methods that had proven successful over Europe: dead reckoning, celestial navigation, and visual landmarks when weather conditions allowed. Yet there was something fundamentally different about conducting bombing operations over Japan from such extreme altitudes, and it was undermining the entire system. Reconnaissance photographs revealed bomb craters scattered across rice paddies, residential areas, and uninhabited coastlines. The Nakajima aircraft engine plant they had targeted remained unscathed, while the Mitsubishi factory continued to operate 3 shifts. The statistics were alarming. During high-altitude precision bombing raids in early 1945, only 5 to 10% of bombs landed within 1,000 feet of their intended targets. For comparison, this represented worse accuracy than artillery used during the Civil War. The Army Air Forces dedicated years to the development of the Norden bomb sight, an advanced analog computer designed to accurately drop a bomb into a pickle barrel from an altitude of 20,000 feet. However, the bomb sight proved ineffective if the entire aircraft was misaligned when the bombardier peered through his scope. Japanese war production was expected to be severely hindered by this point. Contrary to expectations, factories were increasing their output. Zero fighters, artillery shells, and naval vessels continued to emerge from industrial hubs that American bombers struggled to hit consistently. The planned invasion of Japan in November 1945 would confront an adversary with significantly greater defensive capabilities than military planners had foreseen. Casualty estimates ranged from hundreds of thousands to potentially millions. Lame was acutely aware that time was running short. The B-29 program had utilized vast resources and political influence. If it failed to produce results promptly, there would be consequences, possibly for him personally. More critically, American ground forces were gearing up for what was anticipated to be the bloodiest invasion in history, and his bombers were expected to weaken Japanese defenses beforehand. This objective was not being met. Unbeknownst to Lame, among his Navigator crews, a select few had discerned the reasons behind the failures occurring at 30,000 feet. They uncovered that an unseen factor was undermining every mission. Furthermore, they devised a strategy to counteract it. This approach contradicted official doctrine, was prohibited for navigators to share with one another, and was deemed dangerous pseudoscience by the higher-ups. Nevertheless, it proved effective. In the desperate spring of 1945, achieving results was the only priority. The method they developed bore a name that resembled meteorology more than navigation: pressure pattern navigation. The individual who pioneered this technique was not an academic theorist or a high-ranking officer. He was a practical navigator who had simply observed atmospheric conditions at altitudes where most airmen had never ventured. Captain Charles Ellington had been conducting B-29 missions from Saipan since late 1944. He had observed something that was not mentioned in the official navigation manuals. Each time his crew flew north towards Japan, their ground speed would significantly increase. Despite the engines operating at the same power settings, during the return journey south, they would struggle through the sky, consuming fuel at an alarming rate. The wind was not merely blowing, it was howling past them at speeds that appeared impossible. What Ellington had discovered was the jet stream, a band of high-altitude wind that meteorologists had speculated about, yet operational air crews had never encountered in substantial amounts. Over Japan, these west-to-east air currents routinely surpassed 200 miles per hour during winter and spring. To provide context, a B-29's cruising speed was approximately 220 miles per hour. Encountering a 200-mile-per-hour headwind meant making minimal progress over the ground. Conversely, flying with it allowed them to reach their target much faster than navigators had calculated. The real challenge was that jet streams were not uniform. They twisted, meandered, and varied in altitude. A bomber formation could have its lead aircraft in winds of 150 miles per hour, while the trailing planes experienced 80-mile-per-hour currents. Even more troubling, the winds were invisible. Crews had no means of knowing they were being pushed sideways across the sky until they looked down and realized their position did not align with their maps. Ellington began to correlate wind behavior with barometric pressure readings and temperature gradients. He observed that specific pressure patterns at altitude could predict where the strongest winds would occur. High-pressure systems generated wind acceleration on their northern edges. Temperature disparities between air masses indicated zones of wind shear. By taking frequent pressure readings during flight and plotting them against forecast charts, he could chart the invisible rivers of wind. This was the essence of pressure pattern navigation, rather than relying on the wind information provided. In the pre-flight briefing, navigators would consistently assess the atmospheric conditions surrounding them and modify their course in real time. A rapid drop in pressure indicated that they were entering a different wind regime. A sudden change in temperature signified that they were crossing a boundary between air masses. By monitoring these variations and utilizing mathematical formulas developed by Ellington, navigators could determine the locations of the strongest winds and either evade or take advantage of them. This technique necessitated additional effort. Navigators were required to take pressure readings every 10 to 15 minutes. They needed to calculate wind drift by obtaining more frequent fixes on landmarks or celestial bodies. They also had to keep meticulous logs of atmospheric conditions and compare them with weather forecasts predicting upper air patterns. This resulted in less time available for other responsibilities and a more cognitively demanding flight experience. However, missions employing Ellington's methods were successfully reaching their targets. News spread discreetly within the navigator community on Saipan and Guam. Some crews began exchanging insights at the officers' club. Ellington started to illustrate diagrams on napkins, elucidating how to interpret pressure trends. A number of navigators began to instruct others in this method during informal sessions between missions. Accuracy significantly improved in squadrons where pressure pattern techniques were adopted. Subsequently, the official channels became aware of this and took decisive action to halt it. The Air Forces had established standardized navigation procedures over many years of training, and the introduction of unauthorized methods, particularly those that contradicted existing doctrine, was deemed hazardous. What if navigators became confused by alternating between techniques? What if the increased workload led them to overlook critical readings? Orders were issued. Adhere strictly to approved methods only. No teaching of unapproved navigation techniques. Anyone found instructing others in pressure pattern methods could face disciplinary measures. Understanding the necessity of the brass band pressure pattern navigation hinges on comprehending the reasons behind the catastrophic failures of traditional navigation methods over Japan. The techniques that functioned effectively at lower altitudes and in European airspace collapsed when B-29s ascended beyond 25,000 feet over the Pacific. In 1945, dead reckoning served as the cornerstone of aerial navigation. The principle was straightforward. Ascertain your initial position, determine your heading, know your airspeed, and compute your expected location after a specified duration. For instance, if you are traveling north at 200 mph for 30 minutes, you should find yourself 100 miles north of your starting point. This fundamental arithmetic had successfully guided ships across oceans for centuries. The critical error lay in the presumption that airspeed equated to ground speed. Airspeed indicates how swiftly one moves through the surrounding air mass, while ground speed reflects actual movement over the Earth's surface. Under calm conditions or consistent winds, one could calculate the discrepancy. However, at 30,000 feet over the Pacific during winter and spring, the air mass itself was propelled by hurricane-force winds. A navigator relying on airspeed for position calculations could be misled by as much as 100 miles after merely an hour of flight, remaining oblivious until spotting the incorrect island below. Celestial navigation offered a supplementary method by measuring angles to stars, the sun, or planets using a sextant. This allowed navigators to determine their position regardless of wind conditions. Although the mathematics involved was more intricate, requiring spherical trigonometry and precise timing, it proved effective, except when it did not. Cloud cover frequently obstructed celestial fixes over the Pacific. Even in optimal conditions, obtaining accurate sextant readings from a vibrating, pressurized aircraft traveling at 220 mph posed significant challenges. Minor inaccuracies in angle measurement could result in positional errors spanning dozens of miles. Moreover, celestial fixes necessitated time for calculation. By the moment one discerned their location from 15 minutes prior, they could have been displaced elsewhere. Radio navigation provided an alternative option. However, coverage across the Pacific was limited. Low-frequency radio ranges could assist aircraft when near land, but the majority of the journey to Japan traversed vast stretches of ocean that were beyond the reach of dependable radio beacons. LORAN long-range navigation was being implemented, yet the number of stations remained restricted, and the system functioned optimally at lower altitudes where signal propagation was more reliable. Visual navigation became unfeasible over Japan, which was blacked out at night. Even during daylight bombing missions, recognizing landmarks from 6 miles above through industrial haze was nearly impossible. Unlike American urban centers, Japanese cities were not organized in neat grids. From extreme altitudes, rivers, coastlines, and terrain features appeared quite similar. Bombardiers looking through their Norden bomb sights often struggled to differentiate one city from another until it was too late. The jet stream exacerbated every mistake. A navigator employing dead reckoning might estimate that he was nearing the target. However, if he had been flying through a 180-meter tailwind instead of the anticipated 80-meter headwind, he would actually be 50 miles past the target. By the time he detected the discrepancy through celestial navigation or visual confirmation, the formation would need to circle back, resulting in fuel wastage and increased exposure to anti-aircraft fire. Formation flying further complicated matters. B-29s conducted bombing runs in formations of 12 to 30 aircraft for mutual protection. Only the lead navigator and the lead aircraft actively navigated, while all others maintained their positions relative to the lead plane. If the lead navigator was off course, the entire formation would be off course, and different aircraft at varying positions within the formation encountered different wind conditions. The orderly box formation that departed from Saipan would become elongated and dispersed by the time it arrived in Japan, rendering coordinated bombing runs unfeasible. Bombing accuracy from altitude relied on the bombardier having sufficient time to properly set up his Norden bomb site. The website required precise inputs: ground speed, wind direction and speed, altitude, and true airspeed. If any of these inputs were incorrect, the bombs would miss their targets. However, at an altitude of 30,000 feet, with winds varying by 100 miles across a single bomber formation, obtaining accurate inputs became a matter of chance. Bombardiers were essentially throwing darts while blindfolded. Pressure pattern navigation functioned by treating the atmosphere itself as a map. Rather than combating the invisible wind currents at high altitudes, navigators learned to interpret, anticipate, and utilize them. This technique was based on principles of atmospheric physics that meteorologists comprehended but had not yet been adapted into practical navigation techniques. The underlying concept was straightforward. Air pressure decreases with altitude, but not in a uniform manner. High and low pressure systems at ground level extended upward through the atmosphere, creating pressure gradients aloft. These pressure variations were the driving force behind wind. Air moved from areas of high pressure to areas of low pressure, but the Earth's rotation altered that flow due to the Coriolis effect, resulting in circular wind patterns around pressure systems. At jet stream altitudes, these winds achieved their peak velocity. The crucial realization was that pressure patterns could forecast wind patterns. By measuring barometric pressure at flight altitude and comparing it to forecast pressure charts, a navigator could ascertain the position of his aircraft in relation to high and low pressure systems. More significantly, he could anticipate how the wind would shift as he traversed different pressure zones. The practical approach operated as follows. Prior to takeoff, navigators examined upper air weather forecasts that displayed anticipated pressure patterns at flight altitude. These forecasts illustrated isobars, which are lines of equal pressure across the Pacific. Where these lines were closely spaced, winds would be at their strongest. Where the winds spread apart, they would be lighter. The jet stream core generally extended along the boundary separating the extremely cold polar air from the warmer subtropical air, characterized by sharp temperature and pressure gradients. During their flights, navigators took barometric pressure readings every 10 to 15 minutes using the aircraft's instruments. Simultaneously, they recorded the outside air temperature. By plotting these readings against time and position, they were able to track their movement through the pressure field. If the pressure was decreasing as they flew north, it indicated they were heading towards a low-pressure system, which suggested that winds would shift and likely intensify. Conversely, if the pressure was increasing, they were nearing a high-pressure zone, which signified a different wind behavior. The significant advancement came from calculating wind drift more frequently and with greater accuracy. Traditional navigation methods required drift readings approximately every hour. In contrast, pressure pattern navigation necessitated these readings every 15 to 20 minutes. Navigators employed drift meters, optical devices that measured the angle between the aircraft's heading and its actual ground track, to ascertain how much the wind was pushing them sideways. By taking frequent drift measurements and correlating them with pressure readings, navigators constructed a real-time representation of the wind field surrounding them. Mathematical formulas enabled navigators to convert pressure gradients into wind speed estimates. The tighter the pressure gradient, determined by the amount of pressure change over a specified distance, the stronger the wind. Temperature data further refined these estimates as temperature influenced air density and pressure relationships. Cold air produced different pressure patterns compared to warm air at the same altitude. By integrating pressure trends, temperature readings, and actual drift measurements, navigators could forecast the wind's behavior ahead of them. This capability allowed them to perform something revolutionary: actively navigate around the most severe winds or intentionally fly through more favorable ones. If pressure readings suggested they were nearing the jet stream core, where winds surpassed 200 ms, they could request an altitude adjustment to either ascend above it or descend below it. If they were flying with a strong tailwind towards the target, they could mark its position and strategize to circumvent it on the return journey, as it would transform into a severe headwind. Implementing strategic wind routing could result in significant savings in flight time and fuel costs. This approach also greatly enhanced bombing accuracy by providing knowledge of the actual wind conditions at bombing altitude, rather than relying on forecasts from hours prior. Navigators were able to supply bombardiers with precise wind data for the Norden bomb site. Rather than estimating that the wind was 80 mobster from the west, navigators employing pressure pattern techniques could inform bombardiers that the wind was actually 165 km per hour from 285 degrees. This level of precision ensured that bombs landed where intended. Captain Ellington had honed these techniques through extensive trial and error across numerous missions. He compared his pressure readings with actual ground positions established by celestial fixes and visual landmarks. He developed tables that illustrated typical pressure patterns alongside their corresponding wind conditions. He also devised simplified calculation methods that navigators could utilize in flight without becoming overwhelmed by complex mathematics. The prohibition on teaching pressure pattern navigation resulted in an unusual circumstance. A method that demonstrably outperformed official doctrine could not be formally shared. Consequently, it went underground. Navigators who had learned the technique from Ellington or independently discovered it began to share it discreetly, away from official channels. The navigator's compartment on a B-29 transformed into a classroom after missions. Between flights, when crews were not resting or writing letters home, small groups convened in Quonset huts on Saipan and Guam. Senior navigators illustrated pressure charts on any available paper. They provided an explanation on how to interpret barometric trends, how to associate pressure drops with shifts in wind, and how to conduct more frequent drift readings without neglecting other navigation responsibilities. These sessions were not formal training. Officially, they were merely experienced crew members offering advice. Unofficially, they were imparting a technique that command had explicitly forbidden. The navigators created a coded language. They did not refer to it as pressure pattern navigation in official discussions. Instead, they spoke of monitoring the barometer, checking temperature trends, or taking additional drift readings for precision. Flight logs documented frequent atmospheric observations, but did not specifically mention the use of pressure pattern techniques. This allowed for plausible deniability. If questioned, navigators could assert that they were simply being diligent with standard procedures. Squadron commanders found themselves in a unique position. Many were seasoned pilots who had completed enough missions to recognize that certain navigators consistently guided their formations to the target, while others meandered across the sky. They observed which crews returned with strike photos depicting bombs on target, and which ones had images of barren countryside. Some commanders discreetly encouraged their navigators to learn from the high achievers, asking no questions about particular methods. Others, constrained by official policy, felt compelled to enforce the prohibition even when they suspected it was counterproductive. The outcomes were more telling than the regulations. By late February and early March 1945, squadrons that had widely adopted pressure pattern navigation were achieving bombing accuracies of approximately 80 to 90%. This meant that 8 or 9 out of 10 aircraft successfully delivered their bombs within effective range of the target. In contrast, squadrons that continued to rely solely on traditional methods struggled to reach 40%. The disparity was so pronounced that crews began requesting transfers to squadrons with superior navigation performance. Lame realized that he did not fully understand the technical intricacies occurring within navigator compartments. However, he meticulously monitored the effectiveness of bombing operations. He observed that certain units consistently outperformed their counterparts. When he inquired with bombardiers and pilots about the reasons for this, they attributed their success to their navigators. The navigators were adept at guiding them to the correct location at the precise moment, enabling bombardiers to fulfill their roles effectively. Intelligence reports derived from submarine reconnaissance and aerial photo reconnaissance indicated a different narrative. Japanese factories that specific squadrons had targeted were indeed destroyed. The Nakajima plant at Musashino, which had been struck multiple times with no significant impact in late 1944, finally exhibited considerable damage following raids in February 1945. The key difference lay in the navigators who successfully directed bombers over the actual targets rather than merely over suburbs located 5 meters away. The Japanese anti-aircraft response also highlighted advancements in navigation. Flak batteries positioned around industrial sites began inflicting heavier casualties on bomber formations, as the bombers were now flying directly over the areas under defense. In a somber manner, The increase in battle damage served as evidence that navigation was improving. Crews were successfully reaching defended targets instead of meandering over lightly defended residential zones. By early March 1945, the underground dissemination of pressure pattern navigation had achieved critical mass. A greater number of navigators were familiar with the technique than those who were not. New replacement crews arriving from the United States found themselves learning this method during their initial missions from seasoned navigators who regarded it as standard practice. Although the official prohibition remained in effect, it had become unenforceable. It was impractical to court-martial half of the Navigator Corps. What pressure pattern navigation required was a compelling proof of concept, a mission so successful that it would compel command to recognize the method's significance. That proof was on the horizon. Lame was orchestrating the most ambitious bombing raid in history, and whether he was aware of it or not, the success of the operation would rely entirely on navigators employing a technique that remained officially prohibited. The night of March 9, 1945, demanded flawless navigation. Lame had made a drastic choice that shocked some of his team. B-29s were set to assault Tokyo at night, flying at low altitudes between 5,000 and 8,000 feet, stripped of most defensive armaments to maximize incendiary payloads. This was contrary to everything the B-29 program had been designed for, necessitating 334 bombers from various bases to converge on a single target area in darkness, release their bombs in a coordinated manner, and exit before Japanese night fighters could mount an effective counterattack. Navigation for Operation Meeting House posed challenges that rendered high-altitude precision bombing straightforward by comparison. The bombers would depart from Guam, Tinian, and Saipan at staggered intervals, follow different routes at varying altitudes, and arrive over Tokyo in waves spaced just minutes apart. The initial wave would mark the target with napalm, creating a cross of fire visible for miles. Subsequent waves would fill the marked area with clusters of M69 incendiary bomblets, each designed to scatter and ignite separate fires that would coalesce into a firestorm. For this strategy to succeed, navigators had to direct their aircraft to precise initial points several miles from the target, then execute perfectly timed runs to the release point. Arriving too early would result in bombing unoccupied areas before the pathfinders marked the target. Arriving too late would mean entering smoke and chaos from hundreds of preceding bombers. Being off course by even a mile could lead to dropping incendiaries on the wrong neighborhood, creating gaps in the fire pattern that would hinder the development of the firestorm. The navigators understood what Lame did not explicitly recognize. Pressure pattern navigation would determine the success or failure of this mission. The flight to Tokyo would traverse multiple pressure zones and wind regimes. The jet stream was active in early March, albeit less intense than during its winter peak. At the lower bombing altitudes prescribed by Lame, the winds would differ from those at 30,000 feet. Yet they would remain significant and unpredictable without adequate atmospheric monitoring. The lead navigators in the Pathfinder aircraft bore the greatest responsibility. They were the first to arrive, flying ahead of the main force to designate the target area. Captain William Benn, the navigator on the lead B-29 Pathfinder, utilized the flight to Tokyo to take pressure readings every 12 minutes while continuously calculating drift. His log documented the systematic use of pressure pattern techniques, recording barometric pressure, outside air temperature, drift angle, and comparing all data against the forecast charts. When pressure gradients suggested an impending wind shift, he modified the recommended heading before the pilot could perceive the change. The strike photography from that night narrates the events. The Pathfinders positioned their napalm crosses within 300 feet of the intended aim point in the Asakusa district of eastern Tokyo. This densely populated residential and small factory area was exactly where LA's planners aimed to initiate the fire. Subsequent waves, guided by the burning crosses and their own navigational calculations, deployed incendiaries in an expanding pattern, and post-mission reconnaissance revealed bomb impacts forming an almost textbook carpet pattern across the target zone. A total of 334 aircraft successfully hit their target that night. Rather than scattered attacks throughout Greater Tokyo, There was concentrated bombing over approximately 16 square miles. The navigational accuracy set the stage for what ensued. A firestorm that reached temperatures exceeding 1800 degrees Fahrenheit, generating winds that drew oxygen from shelters and fire breaks. The flames were visible to B-29 crews from 150 miles away on their return flight. The human toll was staggering, with estimates ranging from 80,000 to 100,000 fatalities in a single night, surpassing the death toll of either atomic bomb. From a strictly military standpoint, Operation Meeting House demonstrated that B-29s were capable of destroying a target when navigators could accurately guide them to the correct location. The industrial capacity of eastern Tokyo was utterly devastated. Factories that had previously avoided damage during earlier high-altitude raids were reduced to ashes. Lame understood the significance of what had transpired, even if he lacked knowledge of the technical specifics. His navigators had successfully delivered the force to the target with an unprecedented level of precision. The method they employed, regardless of its nature, proved effective. Within days, he began to inquire about navigation procedures. Why were certain units achieving greater accuracy than others? What were the high-performing navigators doing differently? The responses led him to pressure pattern navigation. The success of the Tokyo raid was a turning point. Lame could not overlook such dramatic results, and he was not the type of person to allow regulations to hinder victory. By mid-March 1945, he was insisting that his staff examine the navigation techniques utilized by the most precise crews. When the findings indicated pressure pattern navigation, the very technique that had been prohibited, he made a decisively straightforward choice: implement it as official doctrine without delay. The reversal occurred with remarkable swiftness. On March 15, merely 6 days after the Tokyo firestorm, WWII Bomber Command released new navigation directives. While they refrained from explicitly naming pressure pattern navigation, the procedures they prescribed were unmistakable: regular barometric pressure readings during flight, ongoing temperature monitoring, drift assessments every 15 to 20 minutes, correlation of atmospheric data with forecast pressure charts, and real-time course adjustments based on observed wind patterns. Everything that Captain Ellington and his fellow navigators had been clandestinely teaching was now formalized as procedure. Formal training programs commenced immediately. Navigators who had been employing pressure pattern methods for several months transitioned into instructional roles. The same individuals who had previously faced disciplinary threats for instructing on unauthorized techniques were now mandated to teach these methods to every navigator within the command. Classes were conducted continuously on Guam and Saipan, with experienced navigators guiding newcomers through the principles of atmospheric physics, calculation techniques, and their practical applications. The timing was of utmost importance. Lame had progressed beyond the initial experiment conducted in Tokyo. He was strategizing to systematically reduce Japan's industrial cities to ashes, requiring every crew to possess the navigational precision demonstrated during Operation Meeting House. The target list comprised Nagoya, Osaka, Kobe, and Yokohama, all significant industrial hubs that needed to be struck with the same level of concentrated accuracy. The outcomes confirmed the decision within weeks. The raid on Nagoya on March 11th involved 285 B-29s that obliterated the city's aircraft manufacturing sector, with bombing accuracy surpassing 85%. On March 13th, 274 bombers targeted Osaka, again achieving a concentration that would have been unattainable through traditional navigation methods. The strike on Kobe on March 16th attained similar levels of precision. In each instance, post-mission evaluations indicated that bomb impacts were clustered within the target areas rather than dispersed randomly throughout the cities. Japanese war production began its final decline. The raids in March alone either destroyed or damaged facilities responsible for 90% of Japan's aircraft engines, along with significant portions of ball-bearing production, machine tool manufacturing, and electronics. Factories that managed to survive the initial firebombing often found themselves unable to operate due to the destruction of workers' housing and transportation infrastructure. Industrial output that had previously endured ineffective high-altitude precision bombing for months disintegrated under sustained, accurate assaults. The strategic ramifications extended beyond mere physical destruction. Japanese civil defense was unable to manage fires that spread across vast areas simultaneously. Fire departments, which were designed to address peacetime fires or isolated bomb damage, were overwhelmed. Evacuation plans collapsed. The psychological impact on industrial workers was catastrophic. Individuals ceased to report to factories that were potential targets. Even facilities that remained unscathed experienced a significant drop in production as workers evacuated cities or opted to spend nights in shelters instead of resting at home. By May 1945, pressure pattern navigation had become standard operating procedure for all B-29 units. New crews arriving from training in the United States received additional instruction in this technique prior to their inaugural combat mission. Navigation manuals were revised to incorporate atmospheric observation protocols. The method that had been prohibited in January became mandatory by May. The irony was not lost on the navigators who had maintained the technique during the prohibition. They had been vindicated. However, this validation came at the expense of Japanese cities and their residents. The navigational accuracy that contributed to the success of the firebombing campaign also rendered it horrifyingly effective. Between March and August 1945, systematic raids obliterated over 60 Japanese cities utilizing the concentrated bombing patterns facilitated by pressure pattern navigation. The formal adoption of this method did more than enhance bombing precision. It legitimized a novel approach to military navigation that emphasized real-time atmospheric observation over dependence on forecast data. It affirmed the notion that individual navigators assessing conditions during flight could surpass centralized planning. Furthermore, it illustrated that innovation could arise from operational necessity rather than through formal research initiatives. In this instance, however, the innovation had to overcome bureaucratic resistance before it was embraced. The technique that one navigator developed by closely monitoring his instruments had become the cornerstone of American strategic bombing in the final months of the war. The B-29 navigators who pioneered pressure pattern navigation could never have anticipated that their once prohibited technique would influence warfare for the subsequent 80 years. However, the principles they established, real-time atmospheric monitoring, predictive routing based on environmental data, and precision guidance through unseen forces, became fundamental to contemporary military navigation and targeting systems. The immediate post-war effects were evident during the Berlin airlift of 1948-1949. Allied cargo planes were required to adhere to precise schedules and flight paths through narrow air corridors, often under adverse weather conditions. Navigators trained in pressure pattern techniques during the B-29 campaign utilized those skills to ensure the airlift's continuity. They observed atmospheric conditions to forecast turbulence, icing, and wind shear, which facilitated safer and more efficient flights. The success of the airlift owed a subtle debt to the lessons learned over the Pacific. The Korean War witnessed further evolution in pressure pattern navigation. B-29s completed their final combat missions during this conflict, and the navigators aboard employed refined versions of the techniques from 1945. However, the significant advancements occurred with jet aircraft operating at even higher altitudes, where jet streams were more potent and intricate. F-86 Sabre pilots learned to leverage high-altitude winds for tactical benefits, utilizing atmospheric knowledge to extend range or enhance speed over targets. The atmospheric awareness that had been solely navigational during World War II transformed into a combat asset. The development of intercontinental ballistic missiles in the 1950s and 1960s necessitated addressing the same challenges faced by B-29 navigators. How to account for atmospheric conditions over vast distances. Early ICBMs struggled with accuracy because designers initially regarded the atmosphere as uniform. Missile guidance systems that integrated real-time atmospheric data, descendants of pressure pattern principles, significantly enhanced accuracy. A Minuteman missile, for instance, could strike within a few hundred yards of its target after traveling 6,000 miles, utilizing computational descendants of the same atmospheric modeling that Captain Ellington had sketched on napkins. The field of weather forecasting underwent a significant transformation due to the atmospheric data gathered during bomber operations. In World War II, the comprehensive upper air observations obtained from B-29 missions, particularly the pressure and temperature measurements at altitudes that had seldom been sampled previously, offered meteorologists invaluable insights into jet stream behavior. Following the war, meteorological services developed forecasting models that integrated these discoveries. Contemporary weather prediction relies on the comprehension of atmospheric pressure patterns, which are the same patterns that B-29 navigators learned to interpret for their survival. Although the global positioning system, which emerged in the 1990s, may appear unrelated to the navigation techniques of 1945, GPS-guided munitions encounter similar challenges. They must consider atmospheric conditions between the weapon and its target. Modern joint direct attack munitions, which are bombs equipped with GPS guidance kits, utilize atmospheric models to modify their flight trajectories. These bombs assess air pressure, temperature, and wind during descent and adjust their control surfaces accordingly. This navigation based on pressure patterns is applied to a descending bomb rather than an aircraft in flight. Furthermore, drone warfare significantly depends on atmospheric modeling. A Predator or Reaper drone conducting surveillance missions for extended periods must take into account fluctuating wind conditions to remain positioned over a target. The operators in Nevada who control drones over Afghanistan utilize systems that consistently monitor atmospheric pressure patterns and automatically adjust flight paths. The traditional human navigator, who would check a barometer every 15 minutes, has been supplanted by computers performing the same task thousands of times per second. Nevertheless, the fundamental principle remains unchanged. The adoption of these principles in commercial aviation has been more gradual. However, the modern flight management computers installed in airliners perform the same functions that B-29 navigators executed manually. They continuously monitor atmospheric conditions, compare them with forecast models, and modify routing to circumvent headwinds or take advantage of tailwinds. Airlines save millions of dollars each year in fuel expenses by utilizing atmospheric routing, which is a direct application of pressure pattern navigation principles on a commercial scale. The legacy of these techniques extends beyond navigation, offering broader insights into military innovation. Pressure pattern navigation arose from operational necessity rather than formal research initiatives. It was crafted by practitioners addressing immediate challenges rather than by scientists in laboratories. This knowledge spread informally through communities of practice, despite facing official resistance. Ultimately, it was validated by outcomes rather than theoretical frameworks. This recurring pattern of field innovation, informal dissemination, bureaucratic opposition, and eventual acceptance has been evident throughout military history. The navigators who preserved pressure pattern techniques during the months of its prohibition deserve acknowledgement not only for their navigational expertise but also for their belief in the method's efficacy despite official disapproval. They jeopardized their careers by teaching unauthorized techniques because they understood that these methods saved lives and achieved mission objectives. Their readiness to question established doctrine when confronted with reality exemplifies the flexible thinking necessary for winning wars. Today's precision-guided munitions, which strike targets within feet after traveling hundreds of miles, represent the culmination of a journey that began with B-29 navigators striving to hit targets within miles. The transition from one to the other was not linear. It involved bureaucratic conflicts, underground knowledge networks, and techniques that faced prohibition before being validated. This illustrates that often, the most significant innovations arise from individuals willing to prioritize their observations over official doctrine, particularly when lives and missions are at stake.